Good morning, everyone in the North America, and good afternoon, our friends in Europe, and good evening, tinyML to tinyML enthusiasts and experts in Asia. My name is Evgeny Gusev. I am from Qualcomm AI Research and also from the tinyML Foundation, and I'm going to be your host this morning. And it is a great pleasure and a privilege to have a very distinguished person today presenting. It's Professor Vijay Janapa Reddi from Harvard University. Vijay is a very strong enthusiast of tinyML, and he drives a lot of initiatives in this area in the educational space and in the benchmarking space. And that's what Vijay is going to be talking today about tinyMLPerf. So this area started about a year ago when Vijay presented this topic at the tinyML Summit 2020, and now we are very happy to see how this field evolved in a year time frame. A lot of things happened, and that's what Vijay is going to cover in his presentation. Before we start, let me acknowledge our tinyML series, talk series sponsors. It's ARM, the tinyML strategic partner, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, and ThinkSense. And there are additional sponsors available. Contact Olga at tinyml.org for the seminar series. Our next tinyML talk is going to happen after the summit on Tuesday, March 30. And the presenter will be Professor Atlas Won from UT Austin, and he'll talk about the lottery ticket hypothesis for the trained models. As many of you know, we're going to have a great event next week. So next week basically is going to be the tinyML week of the year. It's the summit week. It's going to start on Monday with tutorials, and it's going to end on Friday with the research symposium. All presentations are going to be live. We have quite a few presentations there, very high quality presentations. And despite us being working remotely and being in front of the screen rather than in one conference room, this event is going to be highly interactive. We've done everything possible to make it interactive and live. And thanks to our sponsors, this year event is going to be free of charge. So just go and register there and enjoy the whole week of tinyML state-of-the-art presentations there. And if you're going to miss some of these talks, don't worry, they will be posted as usual on tinyML YouTube channel. Again, a lot of excitement coming up next week. It's full 5 days, starting from 8 a.m. California time, same time live. We are going to have over 70 presentations, 4 tutorials, 2 panel discussions, brand new tinyML research symposium. We'll have 5 papers in the late breaking news, papers from Microsoft, Facebook, Qualcomm, and other companies. We will have awards for the paper, for the product, and for the innovation, the best year awards, and a lot of breakout sessions where people can interact with each other and interact with the experts. So it's going to be really exciting, and we're also very passionate about the new initiative we're going to have on the tinyML for Good live. So again, join it live next week, book your calendar and just enjoy the week there. And the TPC did a great job. The product, the program committee, they've done an amazing job putting this together. And just to show you what's been happening with tinyML in numbers, we started 2 years ago with a small, relatively small event on the Google campus. And now this community have grown to like thousands of people, hundreds of companies, and thousands of people on LinkedIn, Meetup, and YouTube. We started also channels in Asia, like WeChat and Bilibili. So you can see this amazing growth. And thank you for your interest. Thank you for joining this community, and thank you for contributing and building the tinyML and making it really big. And talking about the summit sponsors, I won't be able to go one by one here, but you see There are quite a few sponsors supporting this summit, and we are really grateful for their support, and that's why we can enjoy these free benefits they can provide. So those companies are really the companies who drive tinyML ecosystem and bring new products, new solutions, and it's really exciting to see them supporting the summit. And at this point, again, it is my pleasure to introduce Professor Vijay Janapa Reddi as the presenter. Although Vijay doesn't need to be really to be introduced to this community, he's been extremely active since the very beginning in many aspects of this. He was the driver behind MLPerf. You know, this organization that does benchmarking for AI, very important initiative. And recently, these organizations started doing tinyML benchmarking, working with the tinyML Foundation and other organizations. Then also recently they started a new initiative, ML Commons. So I also encourage you to take a look there. And I am very grateful to Vijay and his colleagues and friends for starting edX classes on tinyML. Those classes, they've been extremely popular with tens of thousands of people joining. It's a really important and very tiny initiative, and Vijay and his team, they're really leading this initiative. Very good initiative for the community. So again, very happy to see Vijay here, and Vijay, please take on from now.
Thank you, folks, for making the time to attend this talk. It's a great pleasure to be here. I'm a very big fan of the effort that tinyML Foundation has been putting in, not only just kind of helping nurture the tinyML community, but also helping the tinyML community sort of see where the future is going. And in that vein, today I'm going to be talking about what it means to look at machine learning system performance, specifically looking at ultra low power machine learning systems, which are pretty much, what tinyML is all about. So the first, I have three fundamental goals in today's talk. First, in order to level the playing field, I'm going to make sure that everybody sort of understands the need to benchmark or do fair and representative machine learning system comparisons. That's the first goal. The second goal is that I'll introduce MLPerf, real briefly explaining how the industry is trying to standardize the benchmarking of machine learning systems. Third is then I'll get into the specifics of tinyMLPerf. As Evgeny earlier mentioned, this is an effort that's been going on for almost a year, almost to exactly just a week off was the last time when I actually presented this, where we were very much in just a conception phase, where we came to the tinyML community and said, hey, let's all get together, people working in the tinyML space, let's get together as a community and try and understand how we can build a benchmark for this particular domain. And I'll talk about the details because there's a number of people who've been working on it. So I'll talk about the specific details in the benchmark, and then we'll wrap it up. All right, getting started, what's tinyML all about? Everybody on this call, by and large, knows that tinyML is really about the intersection between embedded systems and machine learning. Specifically, the way I like to look at it is that it's really about applied machine learning, right? It's because you're taking these machine learning models and putting them onto embedded devices, things that we interact with on a daily basis. Well, there are a large number of different applications that we're all very excited about, all of which are talking about operating within less than like a milliwatt of power, ranging from the kind of devices that you want to interact with on a daily basis, be it Alexa, Siri, or your Google assistants, to just kind of doing intelligent data processing right where things are around the sensor, to more forward-looking applications in the case of like autonomous vehicles, specifically extremely small autonomous and agile vehicles like these small little drones. So we're all super excited about this space, and this is really leading to a boom in terms of the kind of applications that we're seeing and the kind of models that we're trying to shrink down to these extremely small devices. This is all very exciting, but this leads into two fundamental questions that everybody should ask themselves. When it comes to actually building and deploying tinyML, every single one of us, you and me, are faced with the questions of, given a particular task at hand, given some sort of problem that you want to solve, there's a wide variety of different ML systems out there. Almost every week nowadays, I see some sort of new embedded system demonstrating AI capabilities, which is very exciting. Now, while that's exciting, one of the questions that you're going to very quickly run into as you try and build your tinyML applications is, Well, which one of these systems do I actually go with? How do you decide whether system A is better or system B is better? It's actually quite hard, especially in the embedded space. It's extremely hard because the ecosystem is heavily fragmented. Everyone offers very unique solutions. So that's the first problem. Given an application test, how do I figure out which is the right system? The second question is, now given this plethora of different systems, even if you narrow it down into a subset that seem right, how do you know how to compare them? What's a systematic way of you comparing any two systems, right? Now, specifically in the context of machine learning, this becomes extremely crucial, and I want to touch on it. And I'm going to touch on this in the context of just general inference machine learning systems, and then I'll try and narrow it down progressively into the tinyML context. It all comes down to being able to measure things, right? Why are rulers so fundamental? Units, metrics, any sort of measurement unit. Why is it so critical? It's critical because it helps us sort of understand how any two systems compare, right? Imagine if I just come up to you and I say, hey, my number is 2, and my 2 is actually better than 3. Well, I don't know. Is that really true? Well, it kind of depends on what the units are, right? Maybe I'm talking about 2 inches and you're talking about 3 centimeters. Well, that's pretty different. So you really have to kind of knock down a lot of details in terms of what a particular value is. In the context of machine learning systems, these values really are about the performance capabilities and the power efficiency of these ultra low power machine learning systems. So why is that so hard? If I just show you a ruler and I say, well, it's all about measuring things, that might seem quite simple and quite easy. But in reality, when you look at any machine learning computing system. Now, remember, I keep repeating the word system. I don't say machine learning hardware. I don't say machine learning software, because anyone who's working in the machine learning computing stack knows that the outcome that you get in terms of the capabilities of a given system is really a function of all the way from what kind of applications are you running? In other words, what kind of data sets and models are you running, all the way down to what's your actual target hardware. Now, this is a figure that's actually quite complicated, so let me walk you through it in order to help you understand why making sense of machine learning system performance is actually remarkably challenging. This is going to be very much in the general context of machine learning at large. So you're going to be looking at, very big sort of tasks like computer vision, speech, language translation, and autonomous driving. So let's say you know what sort of task you're interested in. Then you go one level deeper. Now, you've got a whole variety of different data sets you might be using. So let's say if I give you a number X and I say, hey, number X is better than number Y. Well, I don't know. It really depends on what are you actually running a machine learning system on? What sort of data set are you using, right? And then of course, there's a question of models. You have many different kinds of models that are out there in the wild. So someone says, again, system X is better than system Y. I don't know. It really depends on what model you're running. And then of course, frameworks play a massively critical role in terms of actually delivering performance. Frameworks perform a lot of different kinds of optimizations that dramatically impact the end result that you see all the way down at the hardware, right? So without stepping through every single one of these, the point that I'm making is that machine learning system stack is actually quite complicated. And it's complicated because of many different models, data sets, frameworks, optimizations, compilers, and so forth. And this cross product that we have here makes it extremely hard to understand what it means when X is said to be better than Y. And if you want to understand the performance of any two systems, then you have to somehow cut through this cross product and really be able to make sense. And that's what I'm going to be getting more into. So the cross product means that you have to be able to systematically answer very specific questions. If I'm comparing system X versus system Y, again, I'm saying system because it's really hardware and software, then you have to know a whole set of answers, like for all of these questions and many, many more. For example, what's the task you're running? Okay, well, you might say, okay, I'm doing something to do with image classification. Okay, well, what's the model that you're running? Is it a ResNet? Is it some sort of simple MLP kind of layer? Or is it something that's actually something more futuristic like ResNext or something like that? And then you have to know about the data sets. And even when you're running that, let's say you kind of lock all of that down, then when you go down to the lower levels, there are lots of different optimizations and scenarios in which you can actually run these inference systems. So you have to kind of know a lot about what is going on underneath the hood in order to be able to measure system X is better than Y, system Y. Now, one of the key reasons you want to be able to do apples to apples comparison is because if we are to move the field forward, it is extremely crucial that we're actually able to fundamentally measure things in a coherent manner. In other words, we can't be saying, I'm comparing apples and oranges. In other words, yeah, they're two fruits. Well, yeah, machine learning. Yeah, they're two different fruits. But you got to be able to do apples to apples comparison in order to be able to say, well, is this system, this new system that came out, is that really advancing the field forward? So that's why being able to systematically measure performance becomes extremely important. Now, in the context of MLPerf, or in the context of tinyML systems, there are a wide range of different kinds of hardware that are coming out. And what we want to be able to do is to be able to say which system is really high performing and which system has less performance. Now, less is not necessarily bad. Less might here be, in the case of performance, it might actually be quite low. Well, but in the case of energy efficiency, this might actually be very high. So we need to be able to sort of dissect those things in a lot of detail. So the key thing becomes we have to be able to come up with a way in order to compare hardware and software. Then we need to be able to standardize this comparison methodology, whatever it is that we create, we need to be able to standardize that across many different use cases and workloads. As I will show you later, in the context of tinyML, there are a wide variety of applications. You and I are all on this call because we're excited about that possibility. But that possibility also kind of makes it hard to create a standardization because there's so many different ways in which you can exercise the tinyML models. So then how do you sort of identify what are the bread and butter pieces of the machine learning stack that you actually want to evaluate? And this has got to be something that everybody's excited about, right? Because it cannot just be any one organization that comes out and says, well, these are the workloads that I care about. Well, I might come over and say, I don't care about your workloads. I care about the workloads that I'm actually running. So then how do you go about actually creating a standard set of use cases and workloads? Then there's a lot of complexity underneath the hood about how machine learning systems run. Given that, then how do you sort of standardize a measurement methodology? To be specific, one example would be, when do I start timing the data? When do I start timing when the inference starts and when the inference actually stops? If you look at any real-world application, it's primarily composed of three fundamental phases. There's a set of pre-processing that you do prior to actually getting things into the neural network. Once it's in the network and it finishes the processing, then you do a bunch of post-processing. Now, typically, we always focus on the neural network side, but in many cases, people also care about the end-to-end performance. So you have to somehow figure out what's a rigorous methodology you can come up with that is uniform enough that it applies to across the entire body of the industry. And one of the critical things that we have to achieve here is that we have to build consensus. We have to bring the community or the industry together in order to drive the industry forward. This is by far the most hardest problem. I think you have to bring communities together to be able to create this blending in order to achieve the end goal of being able to, as a whole, as an industry, being able to measure and compare each other while also being happy that it's meeting the needs of everybody. And that's really where we are today. tinyML is a very unique community because it focuses extremely on ultra-low power systems and it's quite specialized and it's in value add that it brings in. And then there is this notion of MLPerf, which I'll talk about next. MLPerf is effectively a benchmark that the industry has actually built in order to try and address some of the questions that are presented earlier. Now, since it might be new to quite a lot of people, I'm going to touch on the core fundamental principles behind MLPerf, because what we want to do is build a bridge between the MLPerf way of doing benchmarking in order to advance the field with tinyML systems, which have their own unique sort of requirements. So let's get started by answering the question of what is MLPerf. MLPerf is very much like the tinyML community. It is a wide variety of different industry organizations all coming together because they see a remarkable opportunity to be able to advance the field, and they realize that it, as a collective, working together, creating a benchmark, specifically a suite of different workloads, machine learning workloads, that tackle that vertical computing stack that I talked about earlier in a very systematic way. And by doing that, it actually benefits the whole ecosystem. And that's really what MLPerf does. It creates a benchmark. The goals broadly are about enforcing reproducibility in the results. There's a really interesting stat that says only 1 in about 10 papers is actually reproducible out there. So in ML, reproducibility is an extremely critical problem. And if we cannot replicate results, then it's really hard to say is something better than another. Then we have to pick representative workloads, things that people actually care about. If I compare the performance of system X and system Y on a toy problem, do I really care about that? Well, as an end consumer of this sort of data, what I want to see is that we're actually getting results on representative workloads. And it's not about just kind of creating standardization. Ultimately, the number one goal has got to be want to drive innovation forward, right? We want to move the needle forward. And so we have to pick benchmarks and things that push the industry, to challenge the vendors, the silicon vendors and the software vendors to actually demonstrate the best capabilities. And we want to do this in a way that we can actually measure faithfully, that is in a way that is faithful to every single body. And we want to drive both the research organizations and the commercial entities so that everybody's sort of cohesively advancing, because ML is an extremely fast-moving pace. And we want to keep benchmarking affordable because it's got to be something that everybody can take part in. So how do we go about doing this? Because this sort of stencil pattern that I'll show you now is extremely key for building a tinyMLPerf benchmark. MLPerf basically takes public data sets that are available, things like ImageNet, MS COCO, and things like that. And out of that comes out two things: a set of training benchmarks and a set of inference benchmarks. What we care about in this particular talk is really going to be around inference benchmarks. But the guiding principles are fundamentally the same. We seek to identify a set of important ML tasks and models. Then we want to identify how these models are actually exercised in the real world. For example, if you're a smartphone, you might just take a single picture. But if you're an autonomous car, you might actually be looking at pictures that are coming in from multiple cameras, and you need to look at them at the same time. Those are very different scenarios. I'll talk about this in the context of tinyML later. And then we have to identify the right set of rules for benchmarking, provide a clean set of metrics that we will be using to assess, and then we publish the results so that everybody gets to see what the performance of these different systems are. The way to kind of think about it is that everybody gets to show off what the capabilities of their systems are. Now, in the past, MLPerf has done a lot of remarkable work. It's actually progressed from across multiple different versions, v05, v07, and now we're up at v1.0. And there are many different areas we tackle, from vision, language, commerce, and speech. We tackle many different kinds of tasks. Classification, in vision, you have classification, segmentation, detection, and so forth. So across different tasks, we tackle a wide variety of them. We pick representative reference models, things that are actually something that the industry really cares about. We associate them with specific data sets, and these data sets allow us to know exactly how a model was run. And then we set quality targets. Quality targets basically say, for a given benchmark, within what level of performance does a system need to achieve in terms of accuracy? We allow a little bit of flexibility, and these things are built not by any one individual person or entity. It's built as a community consensus, and that levels the playing field across the board. Now, why am I talking about all this? Because the bits and pieces that I'm showing here, the versions, the areas, the specific tasks, the reference models, these are all things that we need to be able to capture in the context of tinyML, which is moving extremely fast. So once we kind of capture that, then we have to have a set of rules that actually govern how we go about doing things. Now, I'm not going to get into the specifics, but I'm just hinting at the possibility that there's a whole different set of submission rules. Exactly how what's the system? Is this a system that is actually publicly available, that is ready for commercial use, or is it a research system that is still in evaluation, but you want to showcase the capabilities that might be coming down the road? And of course, you've got a variety of different inference rules, things about what kind of quantization is allowed. Is retraining allowed or not allowed when you make a submission? Because the way MLPerf works is that we are given a set of reference benchmarks. Now, these are benchmarks that benchmark owners produce, and this code is publicly available to everyone. Then the benchmark people who want to submit, the submitters will take that benchmark and then optimize it to showcase the best capabilities, both from a hardware and software capability. But that has to be done within some confined set of rules. For example, if you're starting to get into retraining, in other words, let's say you do quantization, you go from FP32 to int8. Well, by and large, a lot of people know that when you do this quantization, you're going to lose a little bit of accuracy. Now, I can actually go ahead and retrain the network in order to get some accuracy back. But then if you allow retraining, one of the key things you might get into is that you can start having a very strong ML software team that is actually saying that they can do very good retraining, but then you are claiming something on a system side saying, well, my hardware performance is at X, Y, and Z. So then this leads into a debate about, well, is the performance really coming from the software tuning, or is it actually coming from the hardware side? So that's just a sample of the kind of issues that might come around. And therefore, there are a very strong set of rules that we have laid out that as a community, everyone has agreed that are fair and representative. And then finally, MLPerf ends up publishing results. As you can see here, I'm showing you the V07 results across different systems, data centers, edge, mobile. And there are many different submitting organizations, and all the results are made public. At this point, the key takeaway has got to be that you understand what MLPerf does, right? Because these bread and butter building blocks are what we will be translating over to the tinyMLPerf context. One of the nice things about having all these results out there is the fact that at this point, we have over 1,800 reproducible results coming from over 60 different machine learning systems. And if you look at the range of capabilities that are there in terms of performance, it's almost like a 4 order or so magnitude difference in the ML system performance across a range of different models. So what I want you to take away at this particular point is that having a clean set of rules, having a clean set of models, having a clean set of identified quality, minimum quality targets you have to get, allow you to do head-on comparisons between any two systems. And that's really important to be able to drive the industry forward. In fact, while I'm not showing here, one of the key things that we observed is that just between two submission rounds for a given system, the performance increased quite dramatically because people really pushed their software, their inference framework optimizations quite a bit. And that's just an example where, because now we've got a ruler that we're actually measuring things against, people are forced to kind of push themselves to actually deliver the best result possible. And that's a positive result because as a result of comparing, we're advancing the industry forward. Now that's all great, but when we talk about inference specifically, inference is extremely widespread. And in the context of tinyML, we really care about inference. We're not going to be doing training anytime soon on tinyML devices. Because the inference landscape is so large and wide, going all the way from data centers to autonomous vehicles to edge data centers to smartphones, all the way down to IoT systems, there is no one-size-fits-all benchmark. Therefore, what we have to do is really think about, while we have built all this ecosystem, the industry has kind of built this ecosystem of benchmarks, we have to really kind of ask ourselves what's unique about these endpoint devices that you and I are really excited about, and how can we start driving innovation here forward? I gave you examples saying that in previous generations, we have seen as new versions of the benchmark came, people started demonstrating remarkable capabilities with the same hardware, for instance. And we want to drive that exact same sort of innovation in the tinyML ecosystem. Now, if we look at tinyML, starting off with benchmarks that we have, or application codes that we're all familiar with, like things like CoreMark, MBench, ULPmark. These are traditional embedded system benchmarks. Then, of course, you have machine learning benchmarks like MLPerf, the one I talked about. You have mobile AI benchmark, you have DawnBench, there are a bunch of other benchmarks. But the key thing is that when we look at things in the tinyML context, there's definitely a void. And that's exactly what tinyMLPerf is trying to fill. And now I'm going to start switching into what exactly is inside this tinyMLPerf. So tinyMLPerf's goal is to create a useful benchmark for measuring ML system performance for ultra-low power devices. All right, given that that's our goal, how do we go about this? Let's start off with taking a big picture again. Let's kind of step back from all the rules and all those things that I mentioned. Where is tinyML being used? Well, tinyML's got a wide variety of different applications, largely driven by sensor characteristics, right? So for example, the task category on the left I'm showing you here, you've got audio input, you've got image kind of input, you might have sensors that are giving you telemetry data, any kind of time series data. And then many different kinds of use cases that the industry is really excited about. And a lot of these use cases are being solved by many different kinds of approaches in the machine learning space. I just said machine learning space, not necessarily deep learning only. And then for each one of these tasks, there are data sets that are starting to come out that are representative in some sense for the different machine learning tasks that we want to perform. So then the question becomes, how do we sort of distill these things? Well, question you might be asking is like, well, why is this sort of interesting? Well, there's a lot of stuff we have to do. Even if we identify the tinyML landscape, we cannot just directly go pick the model and then pick the data set and then push it over to the pre-existing MLPerf. Why? tinyML benchmarking needs its own dedicated effort. The community here that's on this call needs to be focused on this because you and I work on extremely different scales compared to the rest of the ecosystem. For example, this is what I'm showing you here are the memory requirements or the memory capabilities of a variety of different devices. For example, the smallest system that we have seen in MLPerf is around 2 gigabytes of main memory. Well, you know what that means. That's a thing that we don't exist in, right? Because we're often playing with memory in the order of kilobytes. So this means that any kind of existing methodology that people have built out there in order to compare two systems is not directly portable and applicable to this kind of context. So we have to engineer, runtimes that actually execute the benchmark. Moreover, if you look at the thing from a perspective of power, in MLPerf, for instance, most of the effort really goes on into benchmarking the performance because most of those systems, while they are concerned about power, they're largely focused on delivering high performance for inference, for instance. So in MLPerf, for instance, you can see the right two bars. The smallest one is about 3.4 watts, which is again a Raspberry Pi. And you can have systems that are in the order of kilowatts, which in the case of NVIDIA systems are really high performance systems. But again, when we are talking about tinyML IoT endpoint devices, we're talking about things that are in the order of milliwatts or less. Typically less than 1 milliwatt is kind of what we really say is a tinyML device. Well, then this begs the question of how do you actually measure power? Anyone who works in this space will say, well, measuring power is extremely complicated because there's so many nuances to how things can actually run. So we got to address that somehow. Then of course, so given that you have this vast space of different benchmarks that are out there, like different use cases that are out there, how do you create a benchmark? A benchmark has got to be something that is subsetted from a large ecosystem and is fairly representative. So we got to ask ourselves in the tinyML context, what is the definition of a benchmark task? How do we sort of pick that particular task as a community? What does performance really mean in the tinyML system? And how do you ensure that the reference implementations that we provide in tinyML are actually applicable when someone actually produces a result? And what sort of optimizations are we going to allow on our tinyML device to showcase the best capabilities? And how do we show results? So these wide variety of questions exist in any benchmark. And what I'm going to talk about soon is the specific benchmarks that tinyML has actually gotten into. Now, one of the key questions before you go on into looking at the benchmarks is really you have to understand how do you subset that vast ecosystem. For example, if I have a machine learning model that's running on a tinyML device, how mature is this machine learning model? There are state-of-the-art tinyML models literally coming out hot off the press pretty much every 6 months nowadays. Right? So then, if for example in the usual case, do you pick something like AlexNet, something that is old and mature? Or do you pick something like ResNet that everybody's excited about, or something like EfficientNet, which is likely to get picked up? Well, the philosophy, you have to have a philosophy for how you actually choose these benchmarks from that vast space, because you have to be able to rationalize the systematic reasoning behind it. So we end up picking benchmarks that are sort of cutting edge, things that are off the academic hot press, but then something that industry is starting to push towards. So nothing at the absolute bleeding edge, not like the very first, the paper that just came out today, but something that industry is actually putting into practice, and that's the maturity. Then there's a notion of variety. What are the different kind of mechanisms you have? In the mainstream, for instance, we have GNMP, RNN, attention-based networks. So you want a potpourri of different kinds of networks because everybody's using different methodologies, different networks for different use cases. So you want to have a benchmark that sort of representatively captures it. Then there's a notion of complexity. How simple is the network and how complex is the network? Not every single deployment in the real world is necessarily using the most complex machine learning model. Might be using something that's quite simple because it's good in terms of the overall efficiency. Then, of course, there's a notion of what's practical to actually have a benchmark. Ultimately, in machine learning, it all comes down to data sets. It's all about the data set. You might think of a model as really exciting, but it's the data set that really gives birth to the models. So you need to have public accessibility to some of these models. All right. All of that said, has been a primer for the specific tasks that tinyMLPerf has actually decided to choose. Now, tinyMLPerf is a working group that actually comes together every single week. And over the last year, what the working group has been doing has been actually working really hard on going through those exact steps that I walked you through. The whole reason I stepped you through MLPerf, how it's structured, to what are the challenges in terms of distilling a large space is all leading to this. What are the tasks? Keyword spotting, visual wake words, anomaly detection, tiny image classification. These are all the tasks that the working group, which is comprised of many different organizations, have come together and said these are the most commonly used tasks. These are mature enough tasks that benchmarking tinyML systems in this effectively kind of gives us a first boost in actually capturing what the diversity looks like out there. So the benchmarks are really built upon the benchmark owners. Now, there's a huge community in the working group that's actually interested in these benchmarks. But at the end of the day, these things are actually built by individuals like you and me sitting behind the scenes and working on it. So I wanted to give a shout out to the people who actually do the heavy lifting. Colby Banbury from Harvard actually leads the tinyMLPerf working group. Java from Digital Capital actually works on one of the core anomaly detection benchmarks. Jeremy Horman, who's actually well known in the tinyML community, actually helps us with the keyword spotting benchmark. Nat Duca from Google works on a visual wakes benchmark, and Pietro also helps contribute to this. And Peter Torelli, who's from Embassy, has actually been a remarkable champion for us. So again, here we're trying to bring the community. There's MLPerf, and Peter Torelli comes from the Embassy side of the world. And one of the key things that Embassy has been very helpful in helping MLPerf understand is that power is obviously extremely key. And how do we go about building not only a performance benchmark, but also a power benchmark? Because these two things have to work together, because at the end of the day, we're talking about ultra low power machine learning systems. And without power, that performance benchmark can actually be quite weak. So I just wanted to give a shout out for the people actually carrying the work out. I also want to mention that Silicon Labs has been very supportive in helping us get the visual wake words benchmark going. So in the context of keyword spotting, for instance, it's all about limited vocabulary. We use a publicly available data set, which is the Google speech commands, and we use a neural network, depth-wise separable convolution network, and Jeremy has been driving this benchmark. And one of the things that's common about this benchmark is that this application is something that's widely used, right? I mean, just think about the number of times, for instance, you say, okay, Google, or you say Alexa, right? It's pretty remarkable. So assessing the capability of this particular application task is it's kind of ubiquitous and makes a lot of sense. Then, of course, there's visual wake words. The notion, for example, is sort of like, is there a person or is there no person? It's a very simple task, but it's also got many different applications in the real world. For example, being able to build devices that are able to say, what's the occupancy in a given room? It's a very simple task, but can actually generate a huge amount of savings in many different use cases, like turning the lights off, for instance, in offices. And Google has been driving this effort. And again, we're building off of the visual wake words data set that Google put forth using a mobile nets model. The third one is anomaly detection, which is looking at time series sort of signals. That's based on the Toy Atmos data set, which is also publicly available. Interesting thing here is we're actually using an autoencoder. So at this point, what I'm trying to hint towards is that we're starting to look at the diversity in the machine learning ecosystem for tinyML. It's not always about just convolutions. It's also about just kind of looking at different kinds of networks. And then, of course, we have the classic image classification application, which we're using the CFAR data set with a simple ResNet 8 model that's driven by the Silicon Lab folks. So how do we actually go about benchmarking? So far what I've kind of mentioned is, these are the benchmarks that we're developing based on all the principles that we're bringing forth from the previous MLPerf sort of effort. But how do you sort of run this? So I just kind of wanted to mention how we actually do this, and this is kudos to the Embassy folks who have been helping build a wrapper around running the MLPerf benchmarks. So the two modes. The first, what I'm showing you here is a simple screenshot that allows you to kind of pick what benchmark you're trying to run, and then set up some sort of configurations, and then allow you to run in order to measure performance. But then there's also the really interesting part, which is we can actually use the same sort of tool and framework in order to collect power measurements. So this way we can effectively get both performance and power data for the systems. We also have a command line sort of interface, but this is the interface that we're trying to promote because it's actually quite easy to use on the devices that we've been looking at. Now, all of that said, great. So now we have a set of tasks. Now we have a mechanism to actually run the tasks where the runner effectively is issuing each of the requests to the inference system to actually do the inference, and then comes back and then overall calculates the accuracy. But as with any machine learning task, some of the interesting problems here are really about understanding what sort of optimizations do we allow. In other words, what are the rules that we want to have for tinyML? What data set in MLPerf, there is a notion of open division and a closed division. Closed division really has a very strict structure around how to run the benchmark. Open division says, go ahead, run the task, solve this particular problem, but solve it in the best way you can, which might mean you might do very different kinds of quantization, you might exploit different kinds of sparsity pruning optimizations. In a limited way, you can do retraining and so forth. So I'm not going to go into each of these details because that would be a lot of detail. But these are some of the things that the working group is actually actively tackling right now. And the benchmark is actually coming out. We can already start taking part in it. The first set of benchmark submissions, as we call it, is going to happen on April 30th. The submission round is basically all about, you have to take the models that we're giving you and then put those models into, you have to take the models and then run those models through your pipeline in order to get the best performance you want. And so we're working with many different member organizations, and there's a process to actually validate the results and then officially publish the results. And one of the key things behind MLPerf is that we often iterate. We get something off the ground, and then we iterate on it. As a conclusion, tinyML is growing and it needs comparability across a wide range of different systems. And the community as a whole is trying to define what are the interesting ML tasks, what are the different data sets and so forth, and trying to establish a clean set of metrics. And as we do this, we all as a community can actually move the needle forward because we will start building systems that are pushing each other to the next level. And with that said, I'm happy to take any questions, and I encourage you to join the group in order to get a bit more information. You can already go to the GitHub and check out the code that's up there. And if you have questions, feel free to reach out to me or Colby, and we'll be happy to connect with you and answer questions.
Okay, great. Thank you, Vijay. I mean, thank you for sharing your thoughts and the latest and greatest about this very important initiative, because definitely the benchmarking and data sets are crucial, I would say, for this industry to unite and move it forward in huge volumes. So there is a question, a couple of questions from the audience. A question from Ali, which is fundamental in a way. So the question is that typically for cloud-based ICs, people use leading edge technologies like 5 nanometer, 7 nanometer, and so on. But for the tinyML type of application, for IoT type of application, there is a variety of technologies people use. People use 4 nanometer, 6 nanometer, 9 nanometer, 65 nanometer, 45 nanometer, and these different technologies. So what is the right metrics there? Because you really need to have the cost in mind as well, right? Because people develop your application for high volumes, low cost, and when you run benchmarking on the 90 nanometer technology versus the cloud-based 5 nanometer, you have this kind of gaps. So what is your thought on this? Like, should cost be included into the equation and be like a cost power type of thing, not just performance at the best technology node?
That's a really good question. I'm not sure, but thank you for asking that question. It is a question that actually sort of permeates very heavily throughout any of the benchmarks that we have created. One of the key things that actually we've been thinking about is that at the end of the day, operators do, especially in the cloud context, they ultimately care about what's that cost value, because that's what's ultimately going to drive the adoption. That said, it's also a very hard metric to kind of really nail down and lock down. So we have yet to adopt that. In the context of specifically around tinyML, it's true that the cost does play a role, but we don't compare the tinyML systems against the larger inference systems. tinyMLPerf is all about just focusing on what this community what you and I actually care about on these endpoint devices. So that effectively kind of scopes things. So we can almost completely erase and forget the rest of the folks, because what we care about is driving this particular ecosystem forward. And to that end, we care at this point only about performance and power. And if this is cost is an interesting metric, then that's something that the working group will naturally discuss, because we're driven by the consensus of the group.
Okay. Yeah. It's still kind of quite challenging question, because again, for practical application, people pick both the cost and the performance question, right? And for benchmarking, obviously, you're going after the performance, and that's a little bit of an unfair comparison in a way.
Yeah.
There is another question from Arugan. The question is, in tinyML benchmarks, it becomes necessary to have different forms of benchmark across multiple levels of compute stack. How do we address consistency when designing benchmark across the multiple levels of compute stacks?
So I need a bit more clarity on that question. So when it says across multiple levels of the computing stack, so when we're looking at performance in the context of tinyML, the working group basically wants to look at the total ML system performance. It's not that we're isolating the hardware. It's not that we're isolating the software. It is the end-to-end system performance. So just having really good hardware alone might not quite pan out, because you're effectively looking at what the software is capable of doing on the hardware, and vice versa. Does that answer the question, Jimmy?
I think in a way, yes, I think. There is another question on the data sets. I think, in my opinion, data sets, as I said earlier, extremely important in making them available publicly. Are there any kind of legal disclaimers, like how people can use these data sets for what purposes and so on? Because that's a very sensitive area, as you know.
Also, a question that is very important. The data sets we have chosen are public data sets. And so there's nothing about the data sets from a licensing standpoint that prevents us from actually being able to use them, because we do want the community to be able to access the benchmark, access the data set in order to run the task. A benchmark ultimately is three components, right? It's the data set, it's the model, and it's the quality targets. So the data set itself has to be public. This is why when you look at the original architecture diagram, block diagram of MLPerf, we say public data sets. And any data sets that we use are all public at this point. And if it is a data set that is part of the benchmark, then it's either we are going to provide it, or it's got to be licensable effectively for use.
Okay. Yeah. And I assume this is like an open license.
Yeah.
Okay.
In the past, what we have done, and I encourage the community to think about this, in the past, what we have actually done is we have actually gotten data sets specifically licensed for the benchmark if we thought that the data set actually made sense. For example, in the inference, when we were doing DLRM, which is a recommendation benchmark that's extremely important to the field, we needed a large enough recommendation data set. And to this end, we went and worked with Criteria Labs in order to get a license agreement that was set up so that we can actually get a representative enough data set to actually benchmark. I'm mentioning that here specifically because if you have an interesting data set that you would like to actually be used in the benchmarks, then please do reach out, because this is something we would like to support. And these things are driven by the initiative of the community.
Okay, great. Thank you, Vijay. There is a question from Amit. Do we have MLPerf benchmarks for vibration, for inertia type of sensors?
At this particular point, I wouldn't say like there's any specific benchmark that we have done yet, but that said, just keep in mind that we're almost at the cusp of sort of the first version of the benchmark. So we're already starting to think about what are the benchmarks that people would like to see. And so if there are benchmarks that you are interested in actually seeing as part of the suite, then certainly that input is welcome.
Okay. Yeah, I think there are so many different use cases there. I think I'm glad that at least the three leading ones, the vision, the audio, and the anomaly, I mean, they're kind of about to start like in a couple of weeks. And then I'm sure there will be more use cases like this, inertia type of sensor, temperature sensing, environmental sensing. There will be all kind of things happening there. But that's a great start. There is another question. Let me see. Yeah, there is a question from Elias. Doesn't the benchmark itself affect the result in both computing and power from the device?
Very good question. Yes, I did not get into the very specifics of exactly how the benchmark is run. So the host system is actually feeding the input data into the system under test. So when we're measuring the power, it's only just the system under test. I should have put in a block diagram of the overall architecture. So we had obviously thought about it. So the benchmark itself does not have that much an effect on the overall ML system performance.
Okay. There is a question from Sandeep, and that's actually also a very good question, is for each particular use case, you pick a particular model. So what he's asking is that for keyword spotting, why is DSCNN preferred to tiny speech attention consider model from one et al, which has high accuracy and smaller model size?
Very good question. This is one of those issues, right, where you have these models that are coming out continuously. And yes, you're absolutely right that we can certainly have a model that has higher accuracy. And I bet you that the second round of the benchmark, because of the input, it's actually going to evolve. So the first benchmark is more about just, you have to think about just trying to get the community together, right? The biggest problem I feel of the first benchmark is not about whether we can create a benchmark. It's about, can you create the consensus first in order to create that inertia that you have to overcome. And so to that end, you want to pick tasks, as I said earlier, that are fairly mature in some sense where people are comfortable. And so that's sort of the what led us into picking the DSCNN model, because it's something that everybody was quite comfortable with and understood. And if you have that understood, then you can build the rest of the infrastructure and ecosystem around it. Because it's not about the models. Very often people confuse the art of benchmarking to be about the models. It's not about the models, friends. It's actually about the rules and the system that you actually build around the model in order to be able to benchmark the performance. That is the hard part. And so once you get that right, then you can swap the models. So in the future iterations, you're spot on. It's highly likely that we might swap the model.
Yeah, no, and I think I assume it's going to be an ongoing effort because there will be new models, newer ways to do things, and different hardware. So I think that's just we are at the beginning of a big journey here, obviously. There is a question from Xiaomin. Are BMW measurement and sub 8-bit inferences also being considered for tinyML? So basically, how do you deal with this reduced bit depth when you do this comparison?
That's a great question. So what we expect is that you can have a quantization method that you want to push. Typically, what we do is we ask the submitters to say, hey, here's a quantization scheme that I'm going to use. So is that okay? Normally, most of the traditional quantization schemes are acceptable. However, you cannot do retraining. There are many reasons I can get into offline. But there's nothing fundamentally limiting anyone from actually doing a certain optimization. If you have to retrain the network, there's a pathway to go into what we call as the open division that I mentioned earlier, where you're just given the task and you can do fairly aggressive optimizations under the set of rules that we have identified for the data set and the model and the task. But you can swap the model, you can do very aggressive optimizations there.
Okay, I think we have time for when there are more and more questions coming, which is great. I mean, definitely it shows that this is a very hot topic for discussion. There is a question. Where is the next question? Yeah, this question from Yushan. At present, tinyML. Nice question. At present, tinyML will be used more in various industrial fields. How does tinyML benchmark play a role in specific industrial fields, such as aircraft, structural failure prediction, for example?
Great question. This goes back to the the wide variety of different tasks that we have to support. What I fully expect is that as time goes by, and as even this particular domain, which today a large number of people think, well, it's tinyML, it's like it's one thing. But it's people like you and me who work in this space know just how widespread this ecosystem can be. So what I naturally expect over time is that we will start specializing in this particular benchmark area where we might say, okay, well, for certain segments of the market, we will end up having special use cases. That's highly possible, but ultimately it really depends on what the community decides that they want to do.
Yeah, definitely agreed. I mean, once we reach a critical mass in a particular use case, I think that would be probably a good time to start a new benchmark in this particular use case when multiple players and high volume of applications there. Yeah, there are more questions here. Well, there is one, I think we'll probably end with this one from Hisham. How I can join the working group? I assume the information here, right? So that's what you have on this page, Vijay.
Yeah, and I want to just explicitly mention that MLPerf is not part of ML Commons, which does more than benchmarks. We actually develop data sets. We actually look at best practices and so forth. I'm mentioning that only because if you talk to most of the folks who are already part of this ecosystem, they'll say, oh, we are a member of ML Commons. Okay, well, member means you're a paying member, and therefore you're allowed to participate in all the innovations that we are working on. However, given that tinyML is a new space, and one of our goals is to help move the industry forward, there is no membership requirement. All you have to do is join the working group, and you can participate in the benchmark discussions that are going on. You can get access to the rules. You can actually submit all free of cost. At this point, the only priority we have is to help the industry kind of jumpstart how they do measurements and comparisons. So it's completely open and public.
Yeah, thank you, Vijay. Well, it is a great question that you and I debate quite often. How do you define a tiny system and make sure we are only benchmarking tiny system rather than comparing tiny against the mighty?
Very good question, indeed. It's the fundamental question, I agree. The way we have thought about it, and this has been based on the input that the community has brought about, is like really kind of looking at what are the models that are in this space and what the use cases look like. And based on that, you sort of draw resource constraints, right? We have not explicitly drawn a box because one of the key things you have to realize is that no one organization, be it MLPerf, be it ML Commons, can dictate what it means to be a tinyML system, because we're not the experts. If you're building a system and you've got a customer and you believe that's a tinyML, well, that's your version or your justification that it is a tinyML system. Who are we to argue with that? Because we're not working with the customer. So to that end, we do not explicitly draw a bounding box. So when you put a system up, all of the specs about your system are shown. So if for instance, I came in and I said, well, here's Vijay's phone, that is a tinyML device, and I have clearly specs that are just absurd. Well, the community is very smart about things. They're going to look at that and be like, well, I don't really care. That's not applicable for me. So to that end, we explicitly allow the community, the submitters, to decide what they believe is a tinyML system. But the specs are all open. So you know the system, you know all the characteristics of the system. You have to submit the metadata that indicates what's inside the system.
Yeah, that's great. Yeah. Really forward-looking question from Ali. So the question is, as federated learning, if federated learning is becoming more interesting and attractive for tinyML type of applications, because we have a lot of these tiny devices that are going to be connected and learning together, are there any plans to have benchmarking for models developed for federated, not just for an individual device, but like for this aggregated type of systems?
Yeah. You got to learn to walk before you run. You got to learn to crawl before you walk. So what I'm saying is that federated learning, in effect, is for me like, you're starting to run. What we're trying to get to is just being able to get up and start walking. So it's natural that the field, as it evolves, we will more than likely end up going towards supporting, these kinds of emerging benchmarks where it's no longer about just an endpoint, but it's actually about a system. But these things take time. So,
yeah, and we are running out of time, Vijay, but I do have many questions here, but I think two of them are quite interesting from the practical viewpoint. One is from the software community and one from the hardware community. So let's start with the software question. How would a pure software developer participate in benchmarking to gauge their implementation? For example, if I have an ML software implementation that I would like to benchmark against, for example, TensorFlow Lite, how do I do it, and what hardware platform would I pick?
I'm so glad you asked the question. It is super important. And very much everybody thinks of these things as just hardware. So in MLPerf, what we have seen in the larger ecosystem is that folks have gone ahead, taken a certain hardware, and then they effectively make multiple submissions. Nothing stops you from making a submission, right? Because it's not like, for example, since you mentioned it, it's not like you can't take a TensorFlow Lite implementation or TF Lite micro implementation and then do a run and then compare it with your software XYZ and say, hey, my performance is so much better. There's absolutely nothing stopping you from doing that. So you can actually make submissions on a given platform that you chose, because we don't specify the platform. You can take that single platform and then make a head-on comparison. And I would strongly, I'm a big proponent of getting software on board, because I do realize that it seems like a hardware benchmark, but this is why right from the beginning I say it's a system benchmark. So pick a single system and then try out the different software frameworks.
Yeah, and this is a fundamental difference between the tinyML perf versus the kind of the cloud-based MLPerf, because you have so much variety of hardware. And related to this, there is a question from the opposite part of the spectrum, from the hardware people. How specific does the hardware specification need to be? For example, if I can submit a benchmark for ARM Cortex M7, or does a specific chip or clock need to be specified? Basically, how detailed do you need to specify it in terms of your cores, how many cores you have, memory, and so on, this kind of things?
Yeah, I would just say that it's a very simple, white paper style specification, right? Nothing that is like super detailed at microarchitecture level, nothing that you're revealing about your secret sauce. We want to support everybody to do their innovations. For example, software, let's say I'm not going to ask you to show me your software internal, not the source code, but what MLPerf will ask you to do is like say that, okay, well, this is a software that we actually officially support for our system X. And so you don't have to reveal the software. It's just saying that this is publicly supported. It's an official version. It's not a benchmark version, if you know where I'm going with that. So that's all that's kind of needed. And similar for the hardware. You just kind of say what the high level specs are that you would tell anybody anyway.
Yeah. Well, there are so many questions, Vijay, from the 300 people who attended this presentation live today, and I'm sure there will be like 1,000 people more watching it on the YouTube later. I think you and I will have to work on this other questions offline and post them on forum. And I think with so much interest and this field evolving so rapidly, probably we should do another kind of follow-up presentation in 6 months or 3 months or whatever, and talk maybe about the specific benchmarks after this three competitions you are starting. And thank you again very much for being here with us today, and thank you for sharing your thoughts. And it's a great progress in a year. It's not a trivial task. It's quite hard to pull these tinyML benchmarks together, given all the diversity of this ecosystem and specificity of different things. But again, you and the team, you've done an amazing job in a year, and I think that's very important for the community. Thank you, and thank you also for sharing this and answering these numerous questions. Again, we'll follow up on this. Thank
Awesome.
you, Vijay.
Thank you. Just want to say thank you very much for Ira, Olga, and Rosina for helping with the whole logistics, because a lot of effort that people also put into running all these tinyML talks. So just a big thanks to the tinyML Foundation, because I think you all are doing an amazing job helping move the industry forward by bringing us all together. So thank you, Evgeny, for leading that effort.
Point once again, I would like to thank our sponsors. ARM, Deep-Light, Edge Impulse, Maxim Integrated, Tixo, Reality AI, and SynSense. And if you're interested in becoming a sponsor for the tinyML Talk series, please contact us. ARM has quite a bit of hardware and IP in the tinyML and software as well. Deep-Light use AI to make other AI faster, smaller, and more power efficient. Tiny Edge Impulse develops tinyML tools for all developers. Maxim Integrated has several products in this space, and most recent one is the Max 78,000 chip. So you can get information on the website there. Kix AutoML and Reality AI that add advanced sensing to your product with Edge AI, tinyML. And since then, that builds sensing and inference hardware for ultra low power sub-milliwatt embedded devices. Again, as a reminder, next presentation will be in 2 weeks as usual, 8 a.m. Pacific, and it's going to be by Professor Wong from UT Austin. And thank you for your attention. And again, we'll see you next week, the tinyML week of the year. It's going to be a lot of excitement, information sharing, networking, interfacing, interacting. Just register and join for free. Thank you. Thank you all.